All right, everyone, so let's go ahead and go over the answers. I'm just going to give them to you right now, and you're going to be checking your work. So we have 219 kilopascals, 6.4 liters. Let's check our work first, and then I can go over a couple questions. 426 milliliters, 88 milliliters, 250 milliliters. However, that is supposed to be 2 sig figs. So a better way to write this is 2.5 times 10 squared milliliters. I guess you also could just put a line under the 5 like that if you wanted as well. Then we've got 1.1 liters. Would anybody like me to do number 7, by the way?
Yes.
Yeah? Okay. Let's do number 7. And then how about we get to 317 milliliters? For fun, shall we do number 4 as well? Okay. For fun, right? Because this is super fun. All right, let's do number 4. Oh, and do you guys all have your answers down and checked your work and all that good stuff? All right, number 4. Ammonia gas occupies a volume of 450 milliliters. Milliliters is a unit of volume. And then at a pressure of 720 millimeters mercury, remember millimeters mercury is a pressure unit, so there's our pressure 1. What volume will it occupy at standard pressure? What volume? Oh, they're looking for volume. That's my question. And at standard pressure, and you're probably like, what the heck is standard pressure? So let me, standard pressure, where is it? Here we go. Standard pressure. Standard pressure is assigned to gases because scientists are like, let's look at the behavior of gases, but let's make sure that we decide a certain temperature and a certain pressure. So standard temperature happens to be 0 degrees Celsius, right? Freezing point of water. And standard pressure is 1 atm, 760 millimeters mercury, 760 torr. Which one shall I choose for this problem? Which unit is my pressure given in? Millimeters mercury. So let's go ahead and use the one for millimeters mercury. So 706. So my standard pressure, let me go back to my, sorry. So standard pressure right here, this is going to be our P2, and standard pressure is 760 millimeters mercury. Again, why did I choose the one that had millimeters mercury? It's because the other pressure was given in that unit. So now I simply am going to use, I want to remind you of the equation right up here. Right, we're going to use Boyle's law equation, the relationship between those two, and we'll plug this in. All right, so P1, we've got 740, let me make this a little bigger, 720, 720 millimeters mercury. That's multiplied by the volume 1, which is 450 with a little decimal there, milliliters. That's important for our sig figs. And then V2 is what we're looking for. We don't know what that is. Our P2 is 760 millimeters mercury. Oh, you know what? Did you guys notice how I just switched P and V? I put the V first and the P second. Does it really matter mathematically? No, because multiplication is commutative, meaning you can change the order. V times P is the same thing as P times V, right? 2 times 3 is the same as 3 times 2. So it doesn't matter. Sorry I switched it. That may have confused you. All right, to isolate V2, we have to remind ourselves what mathematical operation is happening between parentheses? Multiplication. Good. So right now V2 is being multiplied by 760. So to get rid of it, we will divide by 760 millimeters mercury. And before I even do the math, I need to do a stop real quick. Let's make sure I can cancel everything out. So 760 cancels with 760. Millimeters mercury cancels with millimeters mercury. On the left-hand side here, what two things can cancel out there? Millimeters mercury, good. And that's important because then I go, all right, I'm left in units of milliliters, and I say milliliters is a unit of volume. What is it I'm looking for? Oh, V2, oh, a volume. Okay, good. You stop and you have that little mental conversation with yourself, because here's the thing. Your units will always tell you if you've set it up correctly. If somehow, some way, your units do not cancel, then you could stop right then and there and not waste your time doing the math and go figure out how you messed up the setup. Because it's going to happen. You're human. All right, so then you do the math. You do 720 times 450 divided by 760. Now you get an answer, and I just want to, here I'll do it in red. How many sig figs are in 720? Oh, look, I forgot the little period that's right there. Let me put that there. How many sig figs are in 720 now that I have a period? 3. Good. That decimal makes the 0 count. So we've got 3 sig figs here. 450 with a decimal? 3. Now here's something interesting. 760 is a standard pressure. It is defined. If it's defined, it is exact. When we have exact numbers, we don't consider them when we're trying to figure out how many sig figs the answer should be. So in this case, we've got 3 sig figs, 3 sig figs, therefore our answer needs to be rounded to 1, 2, 3 sig figs. Yeah, Manny. Are we good? Probably the most difficult part of that problem was if you didn't know what standard pressure was. And that's fine. I didn't talk about it. You would have had to look it up. All right, let's do number 7. Number 7 reads, chlorine gas occupies a volume of 1.2 liters at 720 torr pressure. What volume will it occupy at 1 atm pressure? I strongly urge you guys to read the question through just once before you start identifying variables. Now we can identify variables. Okay, we got 1.2 liters. Liters is a unit of volume. Yeah, so we got a V1 right here at 720 torr pressure. Oh, it tells you it's pressure, just in case you forgot what torr was. So there's your P1. What volume will it occupy at 1 atm pressure? What volume? Oh, volume, that's what we're going to be looking for. There's our V2. There's our question. And what will it occupy at 1 atm? All right, here is our P2. Anybody notice something about our pressures? They're different units. So when we set this all up and we try to cancel out units, they're not going to cancel. So let's go ahead and convert one of them. Now I showed you guys standard pressure. This one doesn't have standard pressure. Hold on, let's find a better one. This is a good one too. All right, do you guys see that 1 atm is the same thing as, oh wait, hold on, that one isn't good. We need one with torr, right? No, what do we need? Torr. Yeah, 1 atm and 1 torr. Actually, the one I had was good. Well, darn, Miss Vasquez, I changed it. Let's go back. This one, No. There it is. I know that 1 ATM is equivalent to 760 torr. I don't know why we have torr in millimeters mercury and they happen to be the same exact number. It's kind of weird to me. I'm not really sure. I couldn't tell you why. But just know that they're the same. So I feel like it's probably easier. It's probably easier to say 1 ATM is the same thing as 760 torr. So I'm not going to use 1 ATM. Instead, I'm going to use 760 torr. Why? Because this is in torr, this is in torr. Now they'll both cancel. Okay? All right, so let's go ahead and plug that in. We got our pressure 1, 720 torr, times our V1, which is 1.2 liters. That's going to, yep, you're going to step out for a minute? Okay. P2 is 760 torr. I'm going to use that converted amount times V2. What do I do to get the V2 by itself? I will just simply divide both sides by 760 torr. And now before I even do the math, I check. Cancel, 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 cancel. Torrs cancel over here. Had we not converted it, this is where we would have stopped because the top would have been torr and the bottom would have been an ATM and we would have been like, what? It doesn't cancel. So just to give you a heads up, that is why you do this self-check. Now you're left in units of liters. Liters are a unit of volume. Oh, good. That's what you're looking for. Then you do the math. And notice that the answer is rounded to 2 sig figs. That's because 720 is ambiguous. There's no decimal there. So we have to go with the smallest amount, 2 sig figs. 1.2, okay, well those are both non-zero, so that's 2 sig figs. And 760 torr. That was an exact number. That was by definition. Okay? So that's why our answer is 2 sig figs. Are we good to go? All right. So what I'd like to do right now, who's going to remember to turn their homework in? Who's going to help us remember at the end of the period? Akile? And who's going to remind Akile? Nobody's going to help you out. Really? You're going to help him out? Good. Good. Akile's going to remember, be like Vasquez, remind us to turn in our homework at the end because I don't want to disrupt right now. You guys can do that. So what I'd like you to do is get your notes out from yesterday. The ones that looked like this. All right, so I'd like to review with Boyle's law the pattern or the relationship that we saw here. If we saw an increase in pressure, if we saw pressure increase, then, I like if thens, then what happened to volume? Look at our drawings. As we increase the pressure, what happened to our volume? Yeah, Sabrina?
It decreased.
It decreased. Then volume decreased. This type of relationship, and notice I'm writing this in the left-hand side of the margin because that might be a nice place to write this because you have room. So if we see a pressure increase, then we see a volume decrease. Also, we could say vice versa as well. If we decreased pressure, we would have seen an increase in volume. this relationship is called an inverse relationship. If you recall when you did your lab, the graph, sketch a little graph here. So if we have pressure down here, and we're increasing pressure, and we have volume over here on our y-axis, what we saw, if you notice, is a decrease. It's a downward trend. I don't want that to be a straight line. I want it to be kind of curved. There we go. And it is actually kind of a curved line. It's not a perfectly linear. It's curved. Now we're going to look down at Charles' law. So Boyle's law, Mr. Boyle was credited with the relationship between volume and pressure. Mr. Charles here was credited with the relationship that happened between volume and temperature. So before we go any further, what is being held constant? What are the constant? What is not changing if you look at Charles' law? Who has an idea about what's not changing? Raise a quiet hand. Good. We've got Ryan. We've got Sabrina. Maybe Elijah?
No, I was just
No.
spreadsheet.
Okay. Sabrina, what's one thing that's held constant?
From
In Charles' law?
it sort of is that a divide sign or is it just a percentage?
So you
The
have V
fractions
over
are
T. So which variable, what I'm asking is which variable is not involved here? Pressure. Good. So one of the constants is pressure. We are not going to change pressure. Remember, we identify pressure with a P. Ryan, do you know what the other one is? What? Gas particles. Number of particles. Exactly. Number of particles. And remember that we give that an N. Let's think back to our lab. Remember the syringe? And remember the hot water bath the first time you guys used the Bunsen burner? Okay, so we put the syringe in, we put the cap on, we had a certain volume of gas, then we increased the temperature, and what did we notice happened? The volume increased. So the relationship with Charles' law is if we see a temperature increase, then volume also increases. And you can tell yourself the reverse is true if you decrease temp. Remember the can? It was nice and warm. We decreased the temp in the ice bath, and what happened to the volume of the can? It crushed. So it decreased. So we saw that as well. This type of relationship, we call this a direct relationship. If we were to graph it, what the trend line would look like, pretend like the x-axis is temperature, and the y-axis could be volume. And what we see is as we increase temp, we increase volume. This one happens to be a linear relationship, so we do draw a straight line, not a curved line. Try to be engaged, folks. Okay? Try to be engaged. Thank you. All right. A few more things with units. What are the units of volume? Liters. The other type, like, reminder, length times width times height. It would be what? Meters cubed. Yeah, meters cubed. Now, or any variant of that. You could have milliliters, you could have centiliters, you could have decaliters, right? So you could put kiloliters, you could put a prefix in front of liters, and that would be fine. You could also do the same thing with meters cubed. It could be centimeters cubed. I guess you also could see inches cubed, some type of measurement of length cubed. So those are the two types of units you'll see for volume. The units of temp are degrees Fahrenheit, which we rarely use, degrees Celsius, and Kelvin. Now in the gas laws, that's the first lunch, you must use Kelvin for gas laws. And how do you convert that? All right, so because I have space right over here, I'm going to say you take the degrees Celsius, you add 273.15, and what you get is Kelvin. So what you do, and if you notice thermometers, have you guys ever seen a thermometer that measures in Kelvin? I haven't. Yeah. So most thermometers measure in degrees Celsius in a lab. Occasionally it'll be Fahrenheit. If that's the case, you convert Fahrenheit to Celsius and then Celsius to Kelvin. But for the most part, especially in practice problems, you will just have degrees Celsius. And you'll have to add the 273.15, and that will convert it to Kelvin. Let's go ahead and look at our beakers now. Notice the temperatures in Kelvin. We've got 100 Kelvin. So here's our temp 1. Let's pretend like we've got a volume of 20 mils. So our volume 1 is 20 mils, 20 milliliters. Look at, we doubled the temperature. Temp 2. What do you think is going to happen to the volume? I want to remind you of our little graph over here. It's a direct relationship. What are you thinking? It'll increase, yeah. In fact, if we double it, we double the temp, we will just simply double the volume. So 20 times 2 is 40. So our new volume is 40. All right, here's triple, T3. We've tripled the temperature. Hi, dear. Welcome. Oh, okay. Come on over. Maybe you didn't know because you weren't here the other day. So you triple the temp. Can you guys? Yeah. When we triple the temp, we just triple the volume. So we'll go up to 60. Volume 3 would be 60. And then last but not least, if we quadrupled the temp, you guys are getting the pattern, right? We quadruple all right? You see that? You increase one, you increase the other. What I'd like for you guys to do now, is you are going to flip over your paper. There's a practice problem. See where it says Charles Law right here? We're going to do this practice problem, and I'm going to actually, this part where it says you try. So this reads, at 190 Kelvin and constant pressure, a sample of gas has a volume of 32 centimeters cubed. What volume does the gas occupy at 250 Kelvin? All right, so we've got a temperature 1, which is 190 Kelvin. Here's one of the things. Here it looks like here's another one. That's a volume. We've got a second temperature. That's 250 K. And what we're looking for, right, because here's our other one, what volume? Here's the question. Let's go ahead and use our Charles Law equation, which is V1 over T1 equals V2 over T2. And we go ahead and plug that in. So we put 32 centimeters cubed on top, 190 Kelvin on the bottom. V2 is what we're looking for, and T2 is 250 K. When you have a proportion or a ratio or fraction, it's nice because what you do is you guys remember this? You cross multiply. So what do you get? You get V2 times 190K. I'm being very diligent about my units. That's important. And I do 32 centimeters cubed times 250K. By the way, you could have done 250K times 32 centimeters cubed. Doesn't matter because of the commutative property of multiplication. All right, to get the V2 by itself, we'll divide both sides by 190K. And before we go any further, we want to cancel out things and make sure we've set it up correctly. So 190 cancels, K's cancel. Oh, look, on the right-hand side, my K's cancel. This is nice. I'm left in units of centimeters cubed. I asked myself, centimeters cubed is a unit of volume. Oh, good, that's what I'm looking for. And when I do this math, I just simply take 32 times 250 divided by 190. And what I get is 42.1052 and on and on and on and on. I'm going to just go ahead and stop right there. Let's look at sig figs. 32. How many sig figs are in 32? 2. 250? I don't think so.
No, you have 8 minutes.
10 minutes. Okay. All right, 250 has, it's ambiguous, right? So this, we have to go with the least amount to sig figs. 190, also ambiguous. So we'll just go with, right, we just count those two sig figs. Therefore, our answer must be rounded to the least significant figure, which is 2. So there's that. The 1 makes me leave it alone, so it's just 42. And then what are my units? Centimeters cubed. Cubed, not squared. There we go. What I'd like to do right now is pass out the homework to you. And the good news is I have decided, please note in red, do not do the back side. We're only going to do the Charles Law practice today.
I tag rapid on the way.
Let's go ahead and make sure. See the side that says combined gas law at the top of it? Tell yourself, don't do this yet. We're going to do this tomorrow in class. Yeah. What you're going to do is the front part, Charles Law. By the way, that is homework 17. If you don't mind writing homework 17 on top of Charles Law, that'd be great. All right. Let's quickly go through how to do this first problem. A sample of nitrogen gas occupies a volume of 250 mils at 25 degrees Celsius. What volume will it occupy at 95 degrees Celsius? All right, so I have a volume 1 right here. Milliliters, that's a volume. 25 degrees Celsius. There's a problem with Celsius. Remember, we have to add 273, and that's going to give us 298 Kelvin. And that is going to be our temperature one. So look, I just scribbled in the margin my quick conversion. Then I have 195. I need to add 273 to that one. And that is 368 Kelvin. So that's our T2. And what volume? Here's the question. That's the question. What volume? We're going to go ahead and use this equation up here. Notice that on this worksheet, they've rearranged it for you if need be. They also reminded you of the conversion for temperature. So we're going to use this one, V1. We've got 250 milliliters over T1, which is 298 K. Remember, we're always using our temp in Kelvin. Our V2 is what we don't know about, and our T2 is 368 K. I'm going to show you a shortcut real quick. You don't necessarily have to cross multiply unless your variable's in the denominator. Right here it's in the numerator. So I could multiply both sides by 368K, and that's a lot faster. And remember, I stop myself and I cancel everything out, make sure I'm on the right track. My K's cancel. I'm left in units of milliliters. Milliliters are a unit of volume, so I'm on the right track. So on my calculator, I would say 368 times 250 divided by 298, and that's going to give me a volume of 308.724, on and on and on. I need to check my sig figs. Jesse's absent. Yeah, I guess so. All right. I have how many sig figs in 250? Here, I'll do it in a different color so we can see. 250 has how many? 2. It's ambiguous. 368 has 3 sig figs. 298 has 3 sig figs. Therefore, our answer must be rounded to here. So we look at the 7. And our final answer would be 309 because the 7 tells us to move it up. And the units, what are my units? Oh, milliliters. Okay, I'm looking for volume. Milliliters. One last side note. 25 degrees Celsius. If I added 273.15, I want to show you why I just rounded. When I do this, this ends up being 298.15 Kelvin. Why did I just say 298? It's because when I add, I can only show my number to the least significant decimal place, and that happens to be right here. Yes? Because the 7 converted the 8 to a 9? Ooh, you're right. Sorry about that. Wow. So I need to not, here, I'll do it in green. Good call. Mistake. I want to round to here, so I need to look at this number. You're right. So the correct one is 310. But that's ambiguous.
3.1.
Good. So 3.1 times 10 squared. My units are milliliters. Oh, good. On the one that I'm actually recording the video, I've made a nice mistake. Hopefully people can realize that I'm human too, and it happens. Mistakes. They're inevitable. All right. So this is your homework for tonight. Do we have more time here in class?